with the method of undetermined coefficients. This is the important table for Laplace transforms. This one will be on the exam. I will put this on the exam. So again, you should get used to just using this when you're solving your problems. I'll probably have this put up when I'm doing the problems today. But it just basically says function 1 gives you 1 over s, and at is 1 over s. So again, this is the function in the t space, time domain. This is in the Laplace domain. All right? And this shows the different types of functions, shows you some of the important theorems. Let's see, the important one we're going to be using today, let's see, what is the important one I'm going to use today? I guess they don't have it on this table. Okay, we won't do that. We'll talk about it soon. So, well, I'll just remind you, what we had last time was we showed that the Laplace transform of y prime of t was equal to, let me write this as s. Let's let Laplace transform of y of t be equal to y of s. Then this was equal to s, y of s minus y at 0. And we had the Laplace transform of y double prime of t. That one was going to give us an s squared, y of s minus s, y at 0 minus y prime at 0. So that was the important theorem we did last time that we want to use today to solve differential equations. And so again, the whole idea behind Laplace transforms is we start in the t space. We Laplace transform it into the Laplace space. We then do algebraic manipulations to make it into a form which is recognizable on the right-hand side of the equation. Then we invert the Laplace transform to get our solution in terms of the function t. So that's the procedure here. Again, it's purely algebraic using the fundamental theorem of algebra. So let's look at a specific problem. So I'm going to write the problem down here, and then I'll put the table back up. So here's my initial value problem. All of the Laplace transform problems will be initial value problems. So we're looking at the y double prime plus 2y prime plus 5y is equal to e to the minus t. And we've got y at 0 is equal to 1, and y prime at 0 is equal to minus 3. So there is the problem we're working with. Quite obviously, this one could be done by the method of undetermined coefficients. So that would be a technique. On your exam, you will be told, either solve them directly or to use Laplace transforms. If I don't tell you to use Laplace transforms, don't use Laplace transforms. Okay, so again, let me put up for you the table. So, again, we're going to define the Laplace transform of y of t as being equal to y of s, and use this theorem. So we can see, if we do the Laplace, then what we get from this particular one is we just get an s squared, y of s, minus s, y of 0, minus y prime of 0, plus 2 times s, y of s, minus y of 0, plus 5 y of s, right? And that's going to be equal to, from the table, what's e to the minus t give us?
1 over s minus a. Wait a minute, which is just negative 1. So 1 over s plus.
So it gives us a 1 over s plus 1. All right. So now we can see we're going to get s squared plus 2s plus 5 all times this y of s. Right? Then we're going to get minus s from here. Here we're going to get plus 4, and here we're going to get minus 2. Right? 2 times this one. Right? And that's going to be equal to 1 over s plus 1. Okay? So, we can see now that we can write this as y of s is going to be equal to, flipping this over to the other side, we're going to get what? S, so that's going to give us a plus, so s plus 2, so we're going to get an s minus 2, we're going to get s minus 2 divided by this s squared plus 2s plus 5, bringing this over to this side, and then we're going to get plus 1 over s plus 1 times s squared plus 2s plus 5. Oh, whoops, that's minus, this should be plus 3. Thank you. Minus 1, right? There's a plus, there's a minus 3 up there, this becomes a plus 3. Okay? So then, minus 2, that becomes plus 1. Switch it to the other side, this becomes an s minus 1 divided by this particular quantity, and this. Okay? All right. Now, if we put this all over a common denominator of s plus 1 times s squared plus 2s plus 5, then in the numerator, notice we would have to multiply this times s plus 1, right? So this would give us an s squared minus 1, right? And so then add 1 to that, we just get an s squared. Okay? Everybody fine with that? So, as I said, this is just doing algebra. This is just doing algebra. Okay, so the next step, of course, is to use the fundamental theorem of algebra, which is basically the stuff we do, partial fractions, decompositions. So we want to look at the quantity. So notice this quantity right here, as it stands, is not in the table, right? We do not see this in the table. So what we want to do is we want to take this s squared divided by this s plus 1 times s squared plus 2s plus 5 and do the partial fractions decomposition, which you should know what? It's just a constant over s plus 1. And then what do we do with this quadratic? Everybody agrees that's an irreducible quadratic? Irreducible meaning it doesn't factor nicely.
In what?
So we could then write this as what? When I have a quadratic, what do I put in the numerator?
bs plus c?
Okay, bs plus c. Okay? All right. So, when you do partial fractions decomposition, the best thing to do, of course, is to multiply by this denominator. So we're going to have s squared is equal to a times s squared plus 2s plus 5 plus the quantity bs plus c times s plus 1. Right? Now, what what technique would you use to solve this partial fractions decomposition? What would be the first thing you would probably do?
Comparing coefficients.
No, let's not use coefficients first. Substitutions? Is there a nice substitution you would like here?
Oh, -1.
-1 knocks out everything on the B's and the C's, don't they?
Yeah.
All right, so if we choose -1, then what do we get? If we put s equals -1, we're going to get 1 equals a. All right, put in -1 here. You'll get 1 minus 2 plus 5. You get 4, right?
Mhm.
Okay. So that immediately tells us what's a equal to. This is a real hard question. What's a equal to? 1/4. All right. Now let's, so by the way, you can mix and match these different things, right? So you use whatever is going to make your algebra the easiest to find. We're just trying to find A, B, C. You do it the easiest way you can. So now we're going to use your coefficients. How about the leading coefficient, s squared? All right. On the left-hand side, we've got 1, right? On the right-hand side, we've got an A and a B.
Mhm.
So what does that tell us about B?
3/4.
It's 3/4. All right, probably the easiest next thing to do is look at the constant terms, as to the 0 terms. How many on the left-hand side? 0. All right. Let's go to the constant terms on the right-hand side. What do we get here? 5a, okay,
Plus C.
plus c. All right. So what does that tell us that c is equal to?
-5/4.
-5/4. All right. So now we have my A, B, and C, right? So we're now going to come over here. Okay. By the way, I think I'm doing this a little differently than I did in the notes, but that's okay. All right, so we're going to have that y of s can be written as 1/4 divided by s plus 1, right? Then we're going to have plus 3/4 s minus 5/4 times, and I'm going to, now you notice the denominator does not look like things in this table, right?
Mhm.
So what we want to do is complete the square, so we could write that as what? S plus 1, the quantity squared, plus 4, right?
Mhm.
Okay, so we do some more algebra on this. So I'm just going to write this as 1/4 times 1/s plus 1. That's something that's in the table, right? Okay, that's in the table. Now, we're going to do 3/4. Okay, if I have an s there, well, I need an s plus 1, don't I? So I'm going to need an s plus 1 here, all divided by this s plus 1, the quantity squared, plus 4. All right, so now I've used 3/4 here. So then what am I going to have to do?
Take off 2, yeah, divided by the denominator.
All right.
Yeah.
Okay, to get this 5/4, with this 3/4 here, we need -2. Okay? Now we're ready to do the inverse Laplace transform of this y of s. Okay. This becomes what?
1/4 e to the negative t.
So we're going to get 1/4 e to the minus t. Okay, and we're going to get 3/4. Looking at the table entry, where do we see this table entry? Which number? It's number 7, right? And we can see then that's got a minus a, so we're going to get a -1, right? So we're going to get e to the minus t cosine of the b is equal to 2. So we're going to get e to the minus t cosine 2t. And here, where's that table entry? Six. It's the shift theorem. So this, by the way, is our shift theorem. We multiply by the exponential to get that shift in there. And so we're going to get, again, we're going to get minus, in this case, e to the minus t, and then e to the minus t sine of 2t. Okay? And so we can, and that is the answer to this initial value problem. So the nice thing about Laplace transforms, you perform the algebra, you put it into recognizable elements in the table, you invert, and you have your function t. So this is y of t is equal to the inverse of all of this. So there is my solution.
That's pretty cool.
Okay, so hopefully I didn't do any algebra mistakes there. Go through this to make sure I didn't miss anything. Okay. All right. By the way, I notice I did a, you can do your partial fractions decomposition instead of putting b s, you can put the b s plus 1. So there's many equivalent ways of doing this. But the reason Laplace transforms are used is it transforms the equation, again, from a differential equation to an algebraic equation. Do your partial fractions decomposition, which is an algebraic manipulation, and then invert back, so you basically, you've got to make sure they match the elements on the table. Not almost match, exactly match. Nice thing about this is what? It also even gave me my coefficients. I didn't have to solve for the coefficients using the initial conditions. Okay? So it took care of the entire initial value problem just by doing algebra. Okay? Any questions on what I did there? Okay. Oh. There's one more theorem here in the sense that if f is piecewise continuous, it's exponential order, exponent a, then if you take the Laplace transform of t to the n, f of t, it just becomes the nth derivative of the Laplace transform as minus 1. And this one's not that useful, though it's, I think it's on the review sheet to use this particular one. So the review sheet has, as you look through this, which is just integration by parts. And you end up with, so you get a very useful category. Laplace transform of t to the n is n factorial over s to the n plus 1. Okay, so that's it. This one, let's move on to the next one. I'm going to go fairly quickly through the theoretical part because I want to show you the more solving another different differential equation. So, one thing again, the Laplace transform is an integral transform. Integrals don't worry about individual points. So, if f of t and g of t are piecewise continuous, if the Laplace transform of f equals the Laplace transform of g, then f and g, where they're continuous, they are identically the same function, and they can only disagree at points of discontinuity. So that's all, that's just what we would hope. There's some uniqueness on this. And what's important, of course, is we can go forward into the transform space and we can go backwards into the transform space. So we have this function f of t. It will agree with f of t up to points of discontinuity there. And those points of discontinuity you don't worry about because they're just individual points. So that makes it useful for being able to transform back and forth between problems and get solutions like we just did for this initial value problem. We saw the last time that we have linearity of the Laplace transform. We use the linearity of Laplace transforms on this differential equation. So this just says, okay, the inverse Laplace transform itself has linearity. Okay, so that's nice. And we did that when we inverted this. We took this one and did them piece by piece. That's just basically the linearity of the inverse Laplace transform. So if we've got this particular one, okay, what you want to do with this particular one is you first get each of these elements to look like elements on the table. To make it look like elements on the table, we do the following. We need a 3 factorial here, so we have to put a 1/3 in front here. We need a 4 here, so we pull a 3 out there. Okay, we just pull the 5 here and we complete the square in the denominator. Now each of these elements are in the table. Does anybody remember what this one was?
No.
It's like a sine or a cosine.
Okay, we guess
Oh,
which
sine.
one? It's the sine. So this one is sine of 4t. This one, we have an exponential shift. So this one tells us we're going to get an e to the minus 2t, multiplying it. And then if you just think of this as s over s squared plus 1, which one is that one?
6 or
It's
7.
the cosine. Okay, so we're going to get an e to the minus 2t cosine. This one's a little trickier. This one, if you were to just have 3 factorial over s to the 4th, that was from the previous slide, this one would have been t cubed. All right? It's in the table. But now we put this s minus 3, what does that tell us? You shift it. So you would get an e to the 3t times that t cubed. And then, of course, these constants come out in front. And so we can do the Laplace transforms of each of the individual ones. Okay? So that's it. We're taking, so again, the name of Laplace transforms is being able to go back. And that's why I'm saying it's probably a good idea as soon as possible to get yourself a hard printed copy of this, which is going to be on the exam, and know where these elements are and how to go forward to them and backwards from them. And in particular, when you do your partial fractions decomposition, you have to somehow get them to look like these elements. Exactly. Any questions on that? All right, so keep these in front of you when you're doing your homework problems. All right, let's try another initial value problem. Okay. So that first term, so again, we're doing the Laplace transform of y of t is equal to this capital Y of s. All right, so by our derivative formula, what happens to that y double prime? Becomes what?
S squared
An s squared y of s
minus y 0
s y of 0
minus s prime of 0.
y prime of 0. Okay, then we're going to get plus. Notice we only have y. When we Laplace transform it, it's going to give us a y of s, right? Okay, and now we're going to e to the minus t cosine 2t. What does that give us?
2.
Cosine goes to, so if I were to look at, if I want Laplace transform of cosine 2t, what does that one give us?
S plus 1 over S plus 1 squared plus 1.
Well, the cosine 2t just gives us s over s squared plus 4, right? Okay, that's in our Laplace table. So when I then multiply by this e to the minus t, everywhere I see an s, I put an s plus 1. Okay, so then this one becomes over here, just times 1. So it's an s plus 1 divided by s plus 1, the quantity squared, plus 4. All right, I think that was element 7 on the table. Okay, yes?
And that's because it's e to the like negative 1t power, right?
Yes.
Okay.
So that's saying that my a is equaling minus 1 that I put into the formula, which would be s minus a over s minus a, the quantity squared, plus b squared. Okay? And so then we're going to get s squared plus 1. So notice one of the things you get, of course, is the characteristic equation appears in front of your y of s, doesn't it? Using an s instead of a lambda. Then, this minus s, okay, that's just going to be a minus 2s, right? So we're going to get minus 2s. Y prime is 1, so we're going to get minus 1 equals this s plus 1 all divided by s plus 1, the quantity squared, plus 4. Okay. So solving for y of s, all right, it's going to be a 2s plus 1 divided by s squared plus 1 plus s plus 1 divided by the quantity s squared plus 1 times, some square brackets on there, s plus 1, the quantity squared, plus 4. Question?
Would the s for the s that's next to the y of 0 be s plus 1 too? Why not?
No, this is the theorem. The theorem, you missed what I erased over there, but the theorem said that the Laplace of y double prime is equal to s squared y of s minus s y of 0 minus y prime of 0. That's an important theorem we did last time. Okay? And so you have to put this element right here. Now you're right that you might want to use an s plus 1 there, but we don't. We really don't in this case.
Okay.
Because, so I could try to find a common denominator and do all this lovely algebra to get the common denominator and so forth, and get a more complex thing. But what about this right here? Isn't this ready to invert right away? To cosine? Sine. So we can already get the inverse Laplace transform of this immediately let's not bother to complicate it by doing more algebra that we can make more mistakes on. So now we're going to focus just on this piece right here. I'm going to show you a trick that I know from the past. They don't seem to teach you in calculus for some reason. By the way, so the fundamental theorem of algebra is true for in terms of real and complex numbers. Okay. So partial fraction decomposition is just basically another term for the fundamental theorem of algebra. Okay, so we need to take this particular fraction here, take this particular quantity here, and we need to do our partial fractions decomposition on it. So I've got this, set it up, s plus 1 divided by this s squared plus 1. I'm going to go ahead and expand this at this point. S squared plus 2s plus 5. Is that right? Is that what I have?
Yeah.
Okay. All right. So this is of course going to be, well, again, these are both irreducible, right? So we would write this as about as plus b divided by s squared plus 1, and then we're going to get plus cs plus d all divided by s squared plus 2s plus 5. I'm going to be doing this slightly different than what I do in the notes, just to sort of remind you of how you did it in calculus. Again, it might be better to use, instead of a CS, a C times S plus 1. I think that's what I do in the notes.
Is the only way to separate this up with partial fraction decomp, or is this just one technique?
Hmm?
Is this the only way to do this?
This is how you do. This is what partial fractions decomposition
No,
is.
I'm asking, is this the only way to split that up, but by partial fraction decomp? Or is there another, never mind, forget it.
I mean, I could, as I said, multiply this thing out, find a common denominator, and have a different thing over here rather than s plus 1, because I could put that left-hand piece in there.
Oh,
But it's, as I said, I can go straight from here. This one right here is already trivial to produce. It gives you the 2 cosine and the sine. So why complicate things by adding more into it?
okay.
You know, you can easily see the inverse Laplace transform. Now, of course, that's going to add in because this one's going to give us a cosine and this one's going to give us a sine, right? So they all come out there. So multiplying through here, we get an s plus 1 is equal to as plus b times s squared plus 2s plus 5 plus a cs plus d times s squared plus 1. Okay? All right. So one of the things, of course, we could do is we've got 4 coefficients to get from this, right? So we could, and notice the highest order is cubed, so we could do the way you have mentioned here, we could do the cubed, squared, first order, and 0th order one, get the 4 equations and 4 unknowns. So I'm going to do something a little different because I've been talking to you about complex variables before. What happens if I do s equals I? All right? This is one I'm sure most people have not seen. Then this one over here becomes 1 plus I.
Oh, cool.
Right? Over here, we're going to get equals AI plus B. What's I squared?
-1.
Negative 1 plus 5 is 4, right?
Mhm.
Plus 2I. What happens if I put I there?
0.
So I got rid of C and D by doing this one complex substitution. Okay, now, let's look at the real part. Over here, we get 1. What do I get for real over there?
Negative 2a plus
4b.
4b.
Yeah. Okay, what about the imaginary part?
4ai
Plus 2b.
and 2bi.
Right?
4a?
Uh, 4a. Okay, so imaginary part, just 1 there, 4 times A, 2 times B. Right? The real part, you get the 4B, and you get minus 2. Okay, so let's take 2 times this equation and add them. All right, so we're going to get 3 equals 10b. So b equals what? 3/10. All right, and let's, so then let's take minus 2 times this equation and add them. Okay. A equals 1/10. So you can see by just one substitution, I nailed 2 coefficients. Okay. It doesn't always work that way. Well, I mean, it always works that way. It's just that sometimes the algebra is harder. I think everybody should agree that algebra was pretty easy to do. Okay, now we're going to do our favorite things of doing coefficients. All right, how about the s cubed terms? On the left-hand side, how many s cubes are there? How many s cubes do you see over here? 0. All right. On the right-hand side, how do I get s cubed?
AS times S squared and CS times S squared.
Okay, so the only way you can get it is an a, that's the s cubed, and a c. So what does that tell us? C better be equal than negative 1/10, right? All right, probably the easiest thing left over is to do constants. Okay, on the left-hand side, we've got 1. On the right-hand side,
Machine over
5B plus D.
all right? So, what does that tell us about D? Remember, so B is 3/10, that'd be 15/10. Over here, subtract that,
Negative 15/10.
so,
Negative 5/10. Negative 1/3.
so.
Negative 1/2. My bad, my bad.
Okay, it's gonna be equal to 1
Relax.
minus 15/10. Okay, looks to me like minus 1/2. Okay? All right. So, coming back over here, let's see. Okay, so we've got minus 1/10 s over s squared plus 1 there. We're going to get, is it minus? No, it's plus. It's plus 1/10. And we're going to get, so we get plus 3/10 over s squared plus 1. And we're going to get minus 1/10 times s. Okay, let's do that as s, s plus 1. All right, so then we got that minus 1/10. Maybe I better not do that yet. Let me just do that. Let's not try to do all the algebra in my head here. Minus 1/2, all divided by this. I'm going to reconvert it to s plus 1, the quantity squared. Is it s plus 2? No, s plus 1, the quantity squared plus 4. Okay? All right. So this is so this could be written as 21 over 10 s times s squared plus 1. 3/10 and 1, that's going to give us plus 13/10 1 over s squared plus 1. Then we're going to get minus 1/10 times an s plus 1 over s plus 1, the that should be s plus 1 squared plus 4. And let's see, so there's, I borrowed 1/10 from there, so it looks like 2/5 still left over. So it's going to be minus 2/5. No. What am I doing? So I gotta do minus 1/10 minus 4/10. Yeah, there is a 2/5. So we're gonna get a minus 2/5 times, I need that 2. So 1/5, 2 over s plus 1, the quantity squared plus 4. All right. Again, I should have shifted away from this over to this. What I'm trying to do is get my elements to look like these 4 elements here in the table. Okay, so my y of t. What does this one invert to?
Cosine of t.
Okay, so we're going to get 21 over 10 cosine of t. What does this one invert to?
Sorry?
Sine. So it's plus 13 over 10 sine of t. Okay, minus 1 over 10. What does this invert to?
Negative.
E to the minus t cosine 2t. And the last one? Shift theorem. E to minus t sine of 2t. And so we get the complete solution by doing our partial fractions decomposition. See that I do match with what I have in the notes. And as you'll see, here I did a little minor modifications. I did the s plus 1 here, I did the 2 there, so that I matched the table. So you can try to match the table early, or you can match it later. All right. Okay, so I did these different things, did the same complex ones there. And so, there you can see these agree, and so the solutions are going to agree. And again, what's nice about this is it actually shows you go, when you do the inverse Laplace transform, so everybody agrees that was just algebra, and it's kind of messy, but it's algebra. You end up with that algebraic expression that if you match the table, boom, you've got the answer to the initial value problem. We could see, based on the characteristic equation, we would have guessed homogeneous sine and cosine. That's the homogeneous. If you're guessing a solution that has those exponentials like that, you're going to guess an e to the minus t sine and cosine, and you could use the undetermined coefficients to do that. But then you'd have to use the initial conditions to get the arbitrary constants in front of the homogeneous. So the amount of work, it is less work doing the Laplace transforms. But you do need to be comfortable with your method of undetermined coefficients. The partial fractions decomposition. Use your favorite way to do it. Usually a smart substitution will get rid of some of the ones you have to calculate there. But probably the best default is what Evan's saying is just, if you don't have anything else to go by powers. But you can see doing the powers can get kind of messy in itself, right? Look at, you gotta get all of the s squared, you gotta get all of the s to the first, so forth. Usually the two n's are the easy ones to get, the highest power and the 0th power. Those are easy to get. The middle ones do all kinds of cross multiplications, and you can make mistakes there. All right, so we have just solved 2 differential equations. By the way, I will be I'm not going to do the Laplace for systems of differential equations. So next
It
time,
does seem a bit excessive. It does seem a bit excessive.
it's pretty messy. It's basically a great introduction to teach you why to do maple. So I will show you the maple techniques to use for Laplace transforms. I do have the sheets for that. So I'm just going to show you quickly how to do that. And then we're going to learn about the step function. That's the most important thing for Laplace transforms, because up until this point we could not handle discontinuities. We want to be able to handle discontinuities. That's the step function. And so you've got a lot of homework problems in Laplace transforms that do things with the step function. Our series, that's going to be the last 1.5, 2 lectures. Not on the next exam, they're on the final.